When you're talking to a family affected by a recessive disease, it's often necessary to think about the carrier frequency in the general population. That can be calculated if you know the frequency of the particular disease using an equation called the Hardy-Weinberg equilibrium. This clip explains how we work out the carrier frequency using that formula. When we saw the couple with the recessive disease, we said that Dominic had phenylketonuria, so he was bound to pass it on, and that Selina had a 1 in 50 chance of being a carrier because she was from the general population. Have you any idea how you worked that out?
No, in a word.
Okay. Now, the reason it's important is because we get lots of different diseases and people often ask, what's the chance of someone being a carrier of this or that condition? And you can work it backwards from knowing the condition's frequency in the population. There's actually a very famous formula. It's called the Hardy-Weinberg equilibrium. And it's, I'll tell you it and then I'll explain how it works. So the formula is P squared plus 2PQ plus Q squared equals 1, which is a completely unhelpful piece of mathematics. So what it means is that there are 3 types of people in the population. There are the people who don't carry phenylketonuria, there are the people who have phenylketonuria, and there are the people who carry phenylketonuria, where they've got one version of the gene and one working and one faulty copy of the gene. And if the gene has a frequency of 1 in 100, then the chance that you will have 2 copies of it from a gene pool is 1 in 100 times 1 in 100, which is 1 in 10,000. If you have a 1 in 100 gene frequency, the chance of you being a carrier is 1 in 50. Let me explain how that works. I'm going to tell you a true story. About 20 years ago, I was sitting reading the paper when my wife dumped a lot of damp socks in front of me and said, put those into pairs. And I was tired of doing that, and I had a very brilliant idea, I thought. So I went to the shops the next day and I bought a large number of identical pairs of black socks. And I went home, took all my existing socks out, put them away, and I put my identical socks in the drawer, all loose. And I said, I never have to put my socks in pairs ever again, because I just have to take any 2 out and they'll match. Brilliant. Didn't quite work because the dye sort of wears off after a while and they all change colour slightly, but it worked for quite a long time. The only slight problem was at that time I had a job in London quite regularly. I had to catch the 7 o'clock train to London, so I had to get up and get dressed in the dark because Linda wouldn't let me put the light on. And so it occurred to me one day going to the train that I might just possibly get up and put a black sock on one foot but one of my training socks on the other foot in the total darkness, because I had 1 pair of training socks in that drawer as well. And I thought, what's the chance I'd go to London wearing a white sock? So, here we have my sock drawer. And in it are lots of black socks and the occasional white sock. So the question is, what's the chance? If, let's just say, for example, 1 in 20 of the socks in my drawer were white. What's the chance that I would go to London wearing a white sock?
You'd have to take into account.
So that again, there's a 1 in 20.
So 1 in 20 of the socks is a white one.
Yeah.
What's the chance I go to London wearing a white sock?
So is that, well, you've got a 1 in 20 for each foot?
Yeah, that's right. So there's a 1 in 20 chance for having a white sock on your left foot and a 1 in 20 chance of having a white sock on your right foot. There's a 2 out of 20 chance of getting one or the other. That's 1 in 10. It's twice as high, right? So if you put your hand in here and pull out a sock, then it might be a pair of black socks. It probably will be, but now and again you'll pull out a white sock. What's the chance if 1 in 20 socks is a white one? What's the chance of pulling out a pair of white socks?
Is it?
That's hard mental arithmetic. I'll let you off.
1 over 20 times 1 over
Exactly.
20. Yeah.
That's right. So there's a 1 in 20 chance you'll have a white sock on your left foot, and a 1 in 20 chance you'll have a white sock on your right foot. Okay. So there's a 1 in 20 times 1 in 20, or 1 in 400 chance that you would have a pair of white socks on. Now you could get clever and say when you took out the first white sock, you reduced the chance of getting a white sock out of the drawer because there's not as many white socks in the drawer anymore. But that's just being difficult. Let's imagine it's a very big drawer. So then what you're saying is that there's a 1 in 20 chance of having a white there being a white sock, 1 in 400 chance of a pair of white socks, 1 in 10 chance of being a carrier. In other words, if you know how many people get on the train wearing a pair of white socks, if 1 in 400 of the people getting on the train is wearing white socks on both feet, that must mean that 1 in 20 of the socks in the drawer was white. And you can predict
Right.
that
So it has
1
a
in
knock-on
10 of the
effect.
people, you work backwards, right? So if you know how many people got a pair of white socks, you can work out the gene frequency, and from that you can work out the carrier frequency. The square root of the frequency times 2.
Right.
The Hardy-Weinberg equilibrium.